Okay, now we're going to go more into the details of how reinforcement learning works. So there's a family of reinforcement learning algorithms called Q-learning algorithms, which are about, instead of learning a value function, which is to say it tells you the estimated value of being in any state, it instead learns a thing called a Q matrix, or an action value function, which tells you the value of any pair of doing a particular action in a particular state. So suppose we have an MDP, or more generally just some environment with a set of states or observations, which we'll call S, and a set of actions, which we'll call A. So the Q matrix, or the action value function, is supposed to be an estimate of deviating, given the current state, deviating to that given action in the first round, and then afterwards following the optimal policy. So the kind of true Q matrix is defined like that, where it's given by the payoff. So given a state and an action, we get the payoff that we get for following that state, that action in that state, plus the discounted value of the optimal policy. So this is the optimal value function of the next state. And so this is the thing that we're going to approximate. So an actual Q matrix is going to be intended as an approximation of this thing. So this is a function from pairs of states and actions to real numbers, aka an S by A matrix. So this is where the name Q matrix comes from. Okay, probably the simplest method for learning a Q matrix is SASA, which is an acronym that stands for State Action Reward State Action, named after the 5 pieces of data that it uses on every update step. So this is a temporal difference method, but it learns a Q matrix rather than a value function. So like other temporal difference methods, it is appropriate for using in an unknown, potentially unknown environment. So SASA works together with learning a policy. So we need to continually update the Q matrix and the policy together. And then, so the policy is going to be updated always to optimize the action with respect to the current Q matrix. So the update rule is, so if we're in some state S0 and we take some action A, so we're going to be updating Q of S0A. Suppose that we transition to the state S1 and we get a payoff U0, how are we going to update this entry? Well, in a stationary environment, we're going to use this rule. So we're going to get the payoff that we got plus discounted estimated payoff that we will get in the future if in the next round the action we take is what the current policy says to do in the next state. So this is where we use the policy that we're learning alongside the Q matrix. And so just like before for kind of temporal difference value iteration, we can adapt this to work in an arbitrary environment where the rule becomes like this. So when alpha is 1, this thing becomes the stationary version, and we can also vary alpha over time, for example. Okay, so the method which is given the name Q learning, so it's kind of confusing because there are multiple methods for learning a Q matrix, but one of them gets given the name Q learning. So Q learning is a variant of SASA. So again, it's for approximating the Q matrix, but instead of using a policy that it's learning, instead, each update step, it calculates the action that will be taken by the optimal policy in the next state, at least optimal with respect to the current Q matrix. So what that means is, if we're in state S0, we take action A. Suppose we transition to S1 and we get payoff U0. In a stationary environment, we're going to do this thing. So we're going to maximize over the payoffs that we get for all actions that we could do in the next state according to the current Q matrix. And then this is the version for a non-stationary environment. So Q learning is a pretty effective method in practice. This is a very popular method. Okay, I'm going to talk mostly in non-technical terms about a a use case that I find quite interesting, which is algorithmic pricing. So I really like algorithmic pricing because it's a place where AI overlaps with economics, and actually a part of economics where game theory is directly applicable. Algorithmic pricing, as you might know from just background knowledge, is very ubiquitous in a lot of markets. So an example which you're likely to come across in real life is that most products on Amazon have algorithmically set prices. So there's no human anywhere in the loop typically when choosing prices for products on Amazon. There are some other examples which are not like consumer facing, where certain kind of markets have algorithmically set prices. And pricing algorithms are often based on Q-learning. Q-learning just is an effective kind of workhorse method for a lot of things, which includes this. So there's some details. So these algorithms are typically mostly trained offline in a simulated environment, so simulated marketplace. This is like you run a kind of economic simulation of how this thing will behave when you deploy it. So in deployment, generally learning stops, although I think it can continue in some cases. And then in deployment, the competitors are playing literally an economic game. There you have several competitors trying to sell the same product or closely related, what's called substitutable products. And so they're choosing prices, and then buyers, who are typically humans, are going to generally choose the best price. And so you get demand, which is some kind of unknown function of the price, and then the profit that you get is a function of both the demand and the price. So it ends up being a kind of non-linear function of the price. This is kind of economics 101. And a thing which is kind of general knowledge about algorithmic pricing is that they occasionally suffer from kind of emergent runaway behavior, where two or more algorithms get kind of stuck in a loop where they're reacting to each other, causing some runaway behavior. So there was one kind of infamous historical example where a particular book that was nothing special had its price rise from two competitors to about $23 million before any humans could get involved and press stop. And this was caused because one algorithm had a policy to match the price of the competitor, and the competitor, I think something like the book was out of stock, and its policy was to not set it to out of stock, but instead to set the price kind of 20% or something higher than the competitor, in order to disincentivize anyone from actually trying to buy it, instead of marking it as out of stock for whatever reason. And so this caused a runaway behavior. So an interesting topic, which is currently a bit of a hot topic in economics, is something called algorithmic collusion, which is the possibility that reinforcement learning algorithms could be essentially breaking competition law by setting the price higher than it should be. So collusion is a bit of a complicated thing, but to a first approximation, the pricing game has a Nash equilibrium, and so you get the equilibrium price, and under ideal conditions, the market is supposed to give you the Nash equilibrium price, and that's considered kind of fair for consumers. And so when prices rise higher than the Nash equilibrium price, this is when alarm bells ring. So the legal reality is a lot more complicated than this, because there are such things as intent as well. So a couple of years ago, this kind of bombshell was dropped that it appeared that Q-learning algorithms, even very simple ones, under a very wide range of conditions, were learning to do something called algorithmic collusion, where this is kind of implicit collusion where there's no explicit communication. So there's been a lot of follow-up work to this paper. I guess you can read the abstract here. So several people are working on this, including a colleague of mine, Philip Simon, who has recently found, or he believes that this result is not true. And if you look into more details, this goes away. So this is a kind of a bit of a hot topic, and you can kind of imagine there's a lot of money riding on this. So essentially the learned policies are playing a repeated game where they can kind of implicitly send signals to each other by playing moves. And so then the question is like, well, first of all, are they sending signals to each other in a way which is causing them to converge to higher than Nash equilibrium? When I say Nash equilibrium, I mean Nash equilibrium of the stage game. The question is, are they reaching prices which are higher than the Nash in the stage game prices, which is good for the sellers, but bad for consumers and possibly illegal? Although I understand that the legal question is really quite complicated here.